Hi, everybody. We are back and we're here to continue our discussion of regression modeling. And I believe we left off in the last segment looking at this particular example where we were trying to predict operating margin based off of 5 independent variables. And those 5 independent variables were down here. We had competition, which we had some measurement of that, right? The number of competing hotel rooms within a 3-mile radius. We had an awareness metric. How far were people from the nearest La Quinta Inn? There was an office space metric. How much commercial office space was there in the area? We had a median income metric, as well as college enrollment. And we spent a lot of time last segment looking at the statistical output provided to us here and interpreting it. And one of the most important elements to interpret here were the coefficients. These were the B values in particular that we had estimated from the model. And we were able to look at those coefficients and recognize that certain individual parameters were statistically significant, right? Individually significant using that t-test. And we were able to see this very easily by looking at the p-values, right? The p-value on the intercept term was close to 0. And again, as long as that p-value is smaller than like usually the 5% level of significance is what we use. So if the p-value is smaller than that level of significance, okay, then we're rejecting the null hypothesis that parameter estimate is 0. So these are all statistically significant, individually statistically significant effects at the 5% level, with exception, of course, to the enrollment variable we saw last time did not meet that threshold criteria. So enrollment here was individually statistically insignificant. And perhaps we would want to consider eliminating that variable from our model if it's not a significant variable in terms of its predictive power. The other thing you'll notice here, and we didn't talk about this too much last time, but I did want to kind of gloss over it a little bit because it is there, but we're provided confidence intervals. These are upper and lower bounds in the confidence interval. So if you look at this value, 23.2925 and 50.9653, the coefficient estimate in this row actually falls right in the middle of those lower and upper bounds. So the output here is actually providing us the 95% confidence interval bounds on each of these estimates in that first coefficients column here. Okay, so if you wanted to know, how good of an estimate are these point estimates for these slopes and intercept terms, that confidence interval will give you some idea of your error, right? We can see here this point estimate of 37.129. That could really be anywhere between 23.29 and 50.96. There's a little bit of an error, right? A little bit of sample noise in our estimates that we have to be careful about. And that's why constructing confidence intervals is important, because it gives us a little bit of wiggle room to work with it. We also, I think, wrapped up last class discussing another important metric known as the R-squared metric. Okay, and this value directly above it, the multiple R, that's just the square root of that R-squared value. And the way we had interpreted this R-squared value is it told us what percentage of the variation in the Y variable was explained by the fluctuations in the X variables on the right-hand side of the equation. So we can see here in this model, we have just over 50% of the variation in the operating margin from in to in. We have that explained by these 5 variables, including that intercept term there. These 5 variables in our model explain just more than half of the variation in Y. Now, what explains the other half? Well, we left about 48, 49% of the variation in Y unexplained in this model, which means there are other variables we may want to include to increase that explanatory power in some regard here. So we're going to talk a little bit about model selection in this segment. How do I know when I've added the right amount of variables? What metrics can I use to think about this? An important one we're going to come back to in a moment is this metric known as the adjusted R-squared. which actually includes a little bit of a penalty for us doing what's called overcomplicating the model. If we'd introduce too many variables, we make it overly complex. And by complex, I mean there's more B parameters for the computer to have to estimate. Okay, that's a more complicated model. And as we're going to see, more complicated models are very good at fitting data. You can fit the data well, but they're not great at actually predicting on new observations, on data you have not seen yet, which we generally refer to as out-of-sample data, right? You have in-sample data, which you use to build the model, but you have out-of-sample data, which is the other observations you could have sampled from the population, but you didn't. And you want to be good at predicting on everything, right? You don't just want to memorize the practice test that you have and do well on that, right? We want to make sure you perform well out of sample, right, on a test that we did not give you. So we're going to talk a little bit about the adjusted R-squared in a moment. The other metric that I want to spend some time on here in this segment is a metric called the F statistic. And the F statistic, the results for this are displayed in that ANOVA table here. And you'll notice they give us a test statistic as well as a p-value associated with that test statistic. Okay, so there's something called an F test. And the F test is also a way we can think about assessing the efficacy of our model by checking what is known as the joint significance of the model. Okay, and the p-values that we were looking at before, okay, if we go back and we take a look at the p-values that we were looking at in this particular column, these p-values are statistical checks on the significance of the individual variables. Okay, but the F test does something a little different. It actually checks the significance of all the variables together jointly. Okay, and let's go ahead and talk about the F test in a little bit more detail here. So the F test, it is a measure of fit for the regression model. Okay, it's really a measure of joint significance or overall significance of the model. And it basically shows whether or not there is a linear relationship between all of the X variables considered jointly in explaining Y. So the null hypothesis of this test is a little bit strange. Okay, but the null hypothesis says, hey, every single beta, right, every single coefficient on those variables is equal to 0. All right, and if that's true, that means none of the variables are statistically significant in predicting the Y variable. But the alternative hypothesis here is that at least one of those betas is not equal to 0. Okay, at least one. And this is a type of, it's actually a one-tailed test we're going to do here. And the distribution we're going to use is a little bit different. We actually don't have the table for this. If you go online, you can look up the F distribution. You can find an F table. But fortunately for us, the statistical output does provide us the p-value for this test. And we know we're able to reject that null hypothesis here. Right? We can reject this null hypothesis that there is no linear relationship between any of the variables on the right-hand side and the dependent variable on the left-hand side. We can reject that as long as the p-value is smaller than our user-specified tolerance level, our level of significance, which typically is a standard. We're going to use 5% for that. If you want to be a little bit more sensitive, you can use 1%, okay, where you really have to, meet a higher threshold to say that you have statistically significant variables there. But that's, again, a little bit, I think I said more sensitive, but I meant lower sensitivity. We need stronger evidence in that case. So let's go ahead and talk about this F test here. Our null hypothesis is that all of the betas are equal to 0. So recall we had 5 variables in our model. Okay, and we're not actually including B0, the intercept term here, and that is important. But at least one beta not being equal to 0, that's what we are testing against. Okay, and let's go ahead and use that 5% significance level here. So again, the null hypothesis is that there is no linear relationship between competition, awareness, office space, income, and enrollment considered together when using those variables to try to predict La Quinta's operating margin. Okay, and the alternative hypothesis, on the other hand, is saying that any one of those variables, competition or awareness or office space or income or enrollment or some combination, okay, do actually affect operating margin in a predictive sense, in an explanatory sense. So as I mentioned, we are going to take advantage of the p-value approach here. If the p-value is less than the level of significance alpha, okay, then the test is telling us we do have a significant set of variables in our model jointly. This doesn't mean each variable is individually significant, but it means together they all do a good job to some degree at explaining the y variable. So again, we could use the test statistic approach. The only problem with that is we would need that statistical table to figure out the critical threshold values for different levels of significance. And again, we would reject or not reject based on how extreme our test statistic is relative to that critical value. So I will show you what that value is corresponding to the degrees of freedom in this particular model that we're looking at here. But in our example, here is where we are. So our decision rule would be to reject this null hypothesis if the p-value is smaller than 5%. Otherwise, we cannot reject. And the F-test is kind of a little bit different type of test here. This might look like it is a two-tailed test, but it's actually an upper-tailed test related to the F distribution. So you'll notice here in the right diagram, the bell-shaped curve here, it is not quite symmetric. It is skewed. It is positively skewed here according to this F distribution. It's slightly different than the normal distribution, slightly different than the T distribution. So we would need a different table if we wanted to figure out what is this particular critical value threshold, okay, below which we would not be able to reject and above which we would be able to reject, right? We don't really know what that is without using the table. So the p-value is going to be very useful to us here, right? We know if we're using a 5% level of significance, and that is that 5% upper tail probability. So all we have to do now is go back to our statistical output. We can look at either the reported p-value, which showed up in that far right significance column, which I'll pull up in a moment, or we could look at the critical value or the test statistic, the F statistic that's reported, and compare that to the critical value that we would get using an F table, which we do not have here at our disposal, but you could probably find one online pretty quickly. There's probably one in your textbook as well. So let's go ahead and pull up our model to output again and take a look at the p-value associated with our F statistic. So we have that highlighted here in blue. Okay, and you might be reading this and you're like, what does that number mean? Okay, and that number there, 1.36 e to the negative 13, means we actually have a p-value that is extremely small. Okay, that means 1.36 times 10 to the negative 13 power. So if you took that decimal point, you moved it to the left 13 decimal places. Okay, what would you see? You'd see a decimal point, like 12 zeros, and then a 136. It's a very, very small number. Definitely smaller than 5%. Okay, definitely smaller here than 5%. Which means we would reject that null hypothesis. We would reject it. Okay, so this is telling us that our model here, all these variables in our model, what variables are they? Well, all of these guys. Okay, competition, awareness, office space, income, enrollment. Okay, those variables are jointly significant at the 5% level, even though, for example, enrollment here was not significant individually, right? We saw enrollment had a higher p-value. It exceeded 5% on that t-test for individual significance. But this p-value is showing us the joint significance of all of the variables together. So it could be the case that your variables are jointly significant, but none of them are individually significant. And we'll see here in a moment that there is actually an algebraic reason why. I'm not going to prove it mathematically for you. It's in there. You can find it. But I am going to talk about the implication. So let's go ahead and just take a look here at this example of using our p-value approach. And note the test statistic here, 20.1192. That is the test statistic that we would have to check against the critical value if we had that F table and we could find the critical value associated with a 5% level of significance. So let's go ahead and take a look at the p-value approach here. So we have our null and alternative hypothesis. We're using that 5% level of significance in the upper tail. And it turns out, if you go to the F table, okay, you can find that the critical value threshold for our example here comes out to 2.31. Okay, and remember, our test statistic was really high. It was up at like 20.11. So when we look at that test statistic, it definitely falls in that rejection region, which is good, because we also saw that the p-value was extremely small compared to our level of significance. Okay, p-value is smaller. That tells us, okay, that we must be equivalently in the rejection region. So the interpretation here is that the regression model does explain a significant portion of the variation in the operating margin, given that these variables, these 5 independent variables that we use in our model here, are jointly significant. And that is what we were able to show. Now, I want to backtrack just a little bit on some material we talked about in the last segment, which was the R-squared metric, which was a goodness of fit metric. It explains the percentage of variation in the Y variable that is explained by the variation in the X variables. Okay, so let's go ahead and look back at the Model 2 data again. Okay, find our R-squared here. Our R-squared metric is highlighted in blue up there. And it is the sum of the squares from the regression over the sum of total squares, right? So that's why these rows in the ANOVA table here are highlighted. You can take the top row divided by the bottom row. SSR divided by SST will give you this value as well. So again, the way we'd interpret this here is about 51.69% of the variation in the operating margin is explained by the variation jointly in competition, awareness, office space, income, and college enrollment. Now, we can see a couple things. We know the model is jointly significant, and we know at least these variables here, not including enrollment, they are individually significant because the p-values associated with all of these tests are smaller than 5%, which was our level of significance. That's smaller than 5%, smaller than 5, smaller than 5, so on and so forth. Okay, so the model is jointly significant, and variables 1 through 4 are all individually significant. All right, but what we're going to do next is we're going to consider the effects of adding another piece of information, adding another control variable, another regressor on the right-hand side of our regression equation. So instead of having 5 independent variables, we will have 6. And then we can start thinking about comparing 2 models. Model 2, which is a nested version of the bigger model that would also include a 6th variable, which we'll call Model 3 in a moment. Now, a few things to be aware of with respect to this R-squared metric. A lot of people look at the R-squared when they learn regression and they learn statistics, and they kind of use this as their golden rule for how to evaluate a model, and you have to be a little careful. The R-squared tells us how good we fit the data we have. Okay, so how good am I at taking the practice test that I already looked at the answers to, right? That's kind of what the R-squared tells me. It tells me about my in-sample fit, but it does not really tell me about my out-of-sample predictive power. How good would I be actually against the population function, against the data generating process on observations that we haven't included in the sample or that we haven't observed yet? Okay, so a few things you need to know about the R-squared is it's tempting, okay, to make your model overly complex, because if you add more variables to the R-squared, or sorry, if you add more variables to your model, the R-squared will never go down when you add a new variable. Okay, it might stay the same if that new variable really does not have any effect on Y at all. Okay, but it will never go down. Okay, and it can be tempting because of this to think that I should add as many variables on the right-hand side as possible because that'll make the fit in sample go up. And of course it will. The more flexibility, the more parameters you use to define the model, the more flexibility you have to make the model fit every single data point that you want. Okay, so if you add a new variable, okay, there is a loss of something called a degree of freedom, which is really related to complexity of our model. A loss of degree of freedom here means we have increased complexity. There are more parameters we have to estimate relative to the amount of data we have to estimate those new parameters. And the question that we want to think about now is if we add a new X variable, right, it's going to make that R squared go up, but it makes the model more complex. And it turns out when the model's more complicated, I can fit the data better in sample, but it actually is maybe less likely at some level of too much complexity that I'm going to do well at fitting the data out of sample. Okay, so this question of, did the new X variable add enough explanatory power to offset the added complexity that we've created here? Okay, that is really what we want to think about. Okay, did the new X variable add enough explanatory power to offset the loss of a degree of freedom, to offset this increase in complexity? All right, so let me go ahead and show you the statistical output for what we're going to call model 3 here. Okay, so note that model 3, different than model 2, we now have not 5 X variables, but we have 6 X variables. So we didn't get rid of enrollment, which we said we maybe would think about doing if it wasn't individually significant. But we've gone ahead now and we've added this extra variable down in the bottom, which is the downtown variable. And we've added this extra variable down here, a distance to downtown, right? The idea being the closer you are to a consumer center, right? Maybe the more market power you have, the higher you can price and the larger your operating margin might be. So now we've added the 6th variable. And what I want to look at is really all of our metrics in totality here, right? Any one metric alone doesn't really provide you the full context you need to analyze a statistical model. So we're going to look here. First thing we want to note is our R squared in comparison to the model where we only had 5 variables, our R squared has gone up a little bit. Okay, the R squared in the model where we only had 5 variables was a little bit lower, 0.5169, but now it's up to 0.5212. Okay, so it's almost like we're able to explain here a little bit more of the variation in the operating margin. We get about, a little bit less than a 1% gain from adding that downtown variable. Okay. And again, this is the temptation is, oh, well, if I can always make the model fit better by adding more variables, then I'll add more variables. Why not do that? Well, you make the model more complicated, and while it might make for a pretty picture, you're fitting the data well. Okay, it might mean you're not going to generalize on new observations. So if you're building an algorithm with training data, and then you're going to, feed in real time new observations, new customers come to your site and give you new data. And you're going to have to predict on those new data points without knowing what the Y value is for those people, right? You're trying to make a prediction. Okay? Like we pick a new La Quinta location and we build it. Okay? And we have all these input variables. We can try to use that to predict what is the operating margin at that new location before we actually operate that location. Right? We may not perform as well out of sample with a more complicated model. This turns out to be the case. There's a trade-off between what we call model bias and model variance. And if you take a class on machine learning or a more advanced course on data and regression, you would talk about that issue in a fair amount of detail. The other thing I want to note here is let's just go ahead and take a look at which variables in our model are individually significant. So notice the intercept still is, competition still is, awareness is significant, office space is significant, income is significant, but still enrollment fails at the 5% level, also at the 10% level, right? That p-value is bigger than that. And it looks like the distance to downtown is not individually significant either. Okay, and you might be tempted here, and I think if you look carefully, the coefficient maybe doesn't even make sense. It's saying the closer we are to downtown, or sorry, maybe this does make sense actually. The farther we are from downtown, okay, the bigger that distance is, the lower the operating margin is going to be, the less profitable we're going to be. I think that does make sense here, but that value, negative 1.68, that is not statistically significant individually at the 5% level because that p-value on the test is so large. Remember, the rule of thumb we talked about was if you have a test statistic around 2 or larger in magnitude, you're probably going to be rejecting that null hypothesis. And we can see here that test statistic is not bigger than 2, neither is the one on enrollment. But all these other t-stats are definitely bigger than 2 in magnitude, consistent with the p-value results we're looking at here. Okay, the other thing I would like you to see now, since we talked about it, is that the joint model significance is still statistically significant. Okay, our p-value on that joint significance f-test here is 4.37 times 10 to the negative 13. So again, that's like a decimal point. You got 12 zeros and then 437. It's a tiny, tiny number, definitely smaller than 5%. So the model here is jointly significant. We've increased the R squared by adding this variable distance to downtown. Okay, which again, the R squared will never go down when you add another variable compared to the model without that variable. We can see that we have a jointly significant model, and we see that all the individual effects of each individual independent variable are individually significant using that t-test, with the exception of variables 5 and 6, enrollment and downtown. Now, there is this temptation, right? If the R squared only goes up from adding variables, then let's add more variables. Well, we have to be careful because adding more variables, yes, maybe the variable gives us a little bit more explanatory power, but it complicates the model more. We lose a degree of freedom. Okay, and the number of degrees of freedom in the model, let me just mention this now. In a regression model, this is a little bit different than we were just estimating the sample mean. But the degrees of freedom in the regression model is n minus k plus 1, where k is the number of variables, and that plus 1 is there. Okay, what is that plus 1 there for? Well, that plus 1, that is the intercept term. Right, so the total number of b's we have to estimate. We have a b for each variable plus our intercept term. So the degrees of freedom is the number of observations minus the number of parameters you have to estimate. So the more parameters we have to estimate, okay, the more complex the model is, and we lose degrees of freedom. More complicated models have lower degrees of freedom for the same sample size. All right, so fortunately, there is another version of the R squared metric, known as the adjusted R squared metric, that takes into account the degrees of freedom. Okay, and there's a way you can calculate it, and it's actually related to the regular R squared metric. So there's a degrees of freedom adjustment over here that I want you to see, and that is this term right here, n minus 1. Okay, divided by n minus k minus 1. So that is the number of degrees of freedom, right? That is what this is. And what is n minus k plus 1? Well, that's just n minus k minus 1. Same thing. So the denominator there is measuring how much complexity we have in the model. Okay, and the more model complexity we have, okay, the lower the adjusted R squared winds up being. All right. And you can use this calculation. If you know the actual R squared, not the adjusted version of it, it is related. Okay, and you can use this entire calculation to compute the adjusted R squared, but the important elements of the adjusted R squared are as follows. It creates a penalty for excessive complexity in our model. If we're using unimportant independent variables because we were tempted to keep throwing variables in on the right-hand side, okay, then the adjusted R squared is going to start to go down. All right, and it tends to be smaller than R squared. Algebraically, this is going to be true. And it's an alternative method that we can use for thinking about comparing models. So here's what we're going to look at. First of all, let's go ahead and look at model 3 statistical output again. Okay, we know that the actual R squared in model 3 was up here at 52.12%. But the adjusted R-squared, notice, as we had suggested, it is lower. And the way to interpret that here is that the model explains 49.03% of the variation in an operating margin, right? That is explained by all 6 of these variables once we account for the loss of degrees of freedom or the increased penalty for extra complexity in our model. Okay. And what we want to do is we want to think about, well, was model 2 actually better or was model 3 better? Model 2 and 3 were both jointly significant. They both passed that F-test with flying colors. But model 2 had an insignificant individual variable, that was enrollment. And model 3 also has an individual variable that's insignificant, enrollment, as well as the added variable downtown. So the question is, which model is better? And there's a lot of things we can mean by better. By better, we can mean which model fits the data better. And the answer to that is always the more complex model, if you estimate it properly, should always fit the data better. Okay, but we may not be interested in fitting the data in sample. We might be more interested on how well do we predict out of sample on new data points that we have not used to train our regression model, to build the regression model to get those estimates. So let's go ahead and compare model 2, which had only 5 variables. Right, here's model 2, we had 5 variables. And model 3, we had 6 variables. We added that extra distance to downtown variable. And you'll notice, as we suspect, when we compare to model 3, we can see immediately here, right, that when we added the extra variable, the R-squared increases from model 2 to model 3. That R-squared goes up. Okay, model 3's R-squared is larger than model 2's. Right? Model 3's 52.12%, model 2's 51.69%. However, we should also note that the adjusted R-squared are different. Okay, which model has the higher adjusted R-squared? It is actually model 2. Okay, which means that adding that last variable to the model did not contribute enough explanatory power, okay, to offset the penalty for added complexity, for that loss of degrees of freedom. All right, so this is how you can think about comparing models here. You have 2 different models. What happens to the R-squared, which is the one that's better fit for the data, but the adjusted R-squared maybe gives me a little bit more idea of which model is likely to actually perform better out of sample when I'm predicting on data points that I did not use to actually build the estimated regression line itself, or if it's a multivariate case, the regression surface. So there are a few guidelines here. These are just ad hoc rules of thumb based on the number of observations of how many variables that you should include. And there is a conservative estimate here that says n over k should be at least 10. So you have at least 10 variables per independent, you have at least 10 observations per independent variable. Okay, but Dwan's rule kind of relaxes that. And Dwan's rule says you should have at least 5 observations per independent variable. So if I had a regression with 5 variables, let me clear that drawing there, sorry about that. If I had a regression with at least 5 variables on the right-hand side, according to Dwan's rule, I would need at least 25 observations, okay, in order to support that many variables in the model before generalizing might become a problem, generalizing out of sample. Now, the algebraic result that I wanted to discuss here, so the adjusted R-squared, right? That could go up or down when we add another variable. The R-squared, or the multiple R-squared, that will only go up when you add more variables. Okay, but the adjusted R-squared, this will only increase if you add one variable and the t-statistic on that variable is larger than 1. Okay, and I should say here in magnitude, right? Because the t-test, it's a two-tailed test. And so when we say larger than 1, I really mean larger than 1 in absolute value here. Okay, and again, you'll notice the threshold of 1 isn't necessarily guaranteeing that the individual variable that we add, it may not actually be independently significant, right? What was our rule of thumb for the t-test? Well, we said got to be larger than 2 in magnitude. Okay, so the adjusted R-squared may go up even when you add a statistically insignificant variable. That can happen. Similarly, if you add a group of variables, and when adding a group of variables, the adjusted R-squared will only go up if the F statistic for joint significance of the new group of variables is greater than 1. So there's a common theme here, whether it's the F test when we're adding a group of variables or a T test when we only add one variable. If that test statistic is larger than 1, the adjusted R-squared will go up, saying that the model fits a little bit better, even accounting for the added complexity. But it still could be the case that that group of variables that we add, even though they're jointly significant, even though they make the adjusted R-squared go up, they may not be jointly significant in explaining the Y variable on the left-hand side here. This gets a little tricky, right? If we add a variable, it might not be statistically significant individually, but it may provide enough explanatory power to trump the added model complexity and cause that adjusted R-squared to go up. If you see the adjusted R-squared starts to go down like we did when we moved from model 2 to model 3, that's typically a sign that we've added a variable that we didn't need. Okay? So if you're comparing models in your project and you're not sure which model's better, one with fewer variables or one where we added this extra variable, and adding that extra variable causes your adjusted R-squared to go down, that means in some sense the added complexity wasn't worth it. It wasn't worth the additional explanatory power. Now, there is another metric that is important in assessing the fit of a regression model, and that is known as the standard error of the metric. This is the standard deviation of the residuals, really, is what we're looking at here. Standard deviation of the estimated residuals in our regression. And this measures essentially the dispersion of the observed Y values around the values predicted by the regression model. So remember, the sum of squared errors, or the sum of squared residuals, that looked a whole lot like the variance. So if we take that sum of squared residuals, and instead of dividing it by n, we divide it by our degrees of freedom adjustment here, and then we take the square root, we get something called the root mean square error. Okay, it's the square root of the mean square error. Okay, and this is the standard error metric, but utilizing the degrees of freedom in the denominator instead of the total number of observations. So again, SSE here, this is the sum of squared errors. MSE is what we call the mean squared error. We're taking the average of those, but dividing by the degrees of freedom instead of the full set n. And then when we take the square root, we get this whole metric, which is the residual standard error. Here, the standard error of the regression. And this is also referred to as the root mean square error metric for the regression. Now, where do we see that? Well, if we go back to, let's go back to model 2 actually here. We can see model 2, we have a residual standard error of 5.5293, okay, which in some sense means on average, okay, we're about 5.5293% off, okay, either above or below, when we compare the predicted value in our models relative to the actual profit margins in the data. Okay? So that is what that thing means here. And the lower that value is, the better fit the model is. Okay? The smaller that thing is, the better fit the model is. We have smaller residual variance. So again, this indicates the approximate size of prediction errors, and it measures really about how far the Y values are relative to their predictions. If we had a model that predicted perfectly, okay, then Y and Y hat would be the same for every observation, right? The fitted or predicted values would be the same as the actual values, and the standard error metric would be equal to 0 in that instance. Now, the thing to be aware of here is if you have data that's measured in bigger units, like if you convert your units from tons to pounds, where all of a sudden you had a 1-ton vehicle, but now it's 2,000 pounds, and you're trying to predict the weight, okay, that in and of itself will cause that standard error metric to go up, because the standard error depends on the units of measurement of Y, as well as the magnitudes of y in the data. And again, for model 2, we saw that we had the standard error of 5.5293. Okay, and this is giving us some idea about the average prediction error here. Okay, the average prediction error, and these are the means of the different variables in our data set that we've been looking at here. Now, real quick concept check here. If you look at these two pictures, which of these pictures has a larger residual standard error? Well, it's going to be the one where we're not making as good predictions on average, which definitely happens in figure 1. It looks like the data points are all more dispersed around that regression function. Okay, whereas figure 2, the data points are much more clustered around that regression line. Our predictions are better. We can go back to our model selection problem here. We already saw that we had a difference in the adjusted R-squared when we moved from the less complex model with 5 variables in model 2 to the more complex model. Sorry, I'm making the wrong comparison here. Let me change that. We saw that we had a reduction in the adjusted R-squared when we moved from model 2, the less complex model with 5 variables, to model 3, the more complex model with 6 variables. The other thing we can look at here is we could look at the residual standard error. Okay, and you'll note that when we look at the residual standard error, the standard error of model 2 is actually lower than the standard error of model 3. Okay, so when we do this comparison, okay, we now have kind of 2 votes for model 2 being the better model. Okay, the adjusted R-squared from model 2 to model 3 goes down, so that means that extra variable we added in model 3 was no good. And our residuals, on average, our prediction error is lower in model 2 compared to model 3. All right, so model 3 standard error of the regression is larger than model 2's. Okay, and again, that might tell us model 2 is maybe the better model here. Okay, so I want to wrap up with just kind of a summary of these different tools we use for model assessment. Okay, we talked about the sum of squared errors, okay, SSE. That is y minus y hat, the quantity squared, summed over all of our observations. We've just talked about the residual standard error, the standard error of the regression. We discussed both the R-squared as well as the adjusted R-squared, the latter, which penalizes us for added or unnecessary model complexity, including too many variables. And we discussed the significance test, both the p-value of the f-test for joint significance, as well as being able to check the t-statistics and the p-values associated with individual significance for the partial effects that each individual regressor may have on the y variable, on that dependent variable that we are trying to predict. So you can note here, just as we go across the rows here, what corresponds to an ideal fit in the data, or rather for our model. So if we have a perfect prediction here, then we're in a situation where every single data point falls on our regression function. So the sum of the squared errors is 0, our residual standard error is 0, we get a perfect R-squared. Okay, we would wind up getting a near 0 p-value for both the f-test and most likely for the t-test as well. And we have really a perfect model in terms of the fit with the data. I want to be very clear about that. Okay, we're fitting the data well. That doesn't mean we're generalizing well out of sample. The adjusted R-squared will actually help us more in that vein. Now, what happens if SSE is small? This is small, right? R-squared is closer to 1. P-values are small. Well, this is a good model, but you really need to worry that if the sum of squared error starts to explode, okay, meaning as we go down this list, okay, things are actually getting worse, then we wind up in cases where our sum of squared errors is large, our residual standard error is big, the R-squared indicates we're not explaining very much fluctuation in the y variable by considering the x variables in our model, and we're going to be getting p-values on these statistical tests that are very large, indicative of generally poor results, okay, a poor fit in terms of our model fitting the data well. So I want to be clear about this. This is assessing how well the model fits the data in sample. But if you want to get really good at prediction, Okay, and it's not something we're going to focus tremendously on in this particular course or in this particular module here. But if you want to get really good at prediction, okay, then your concern shouldn't so much be your in-sample fit. Okay, but it should be how well do you perform on new observations that you have not used to build the model. And that again is what we refer to as the out of sample error. And this is actually kind of tricky to measure. How do you measure your error on things that you have not observed yet? Okay, and there's actually a nice trick. If you take machine learning or big data analytics, we will talk about a process known as validation, where we kind of use a trick where we hide some data from ourselves. We don't use the full sample to build the model. And then we use the data we hid from ourselves to test the model, almost like we gave ourselves a practice test to build the model with. But instead of giving us the same practice test to test it, we're going to use the data we've hidden from ourselves to actually check the model's performance and estimate that out of sample error. So I hope this was fruitful. That should get you to where you need to be in terms of thinking about model comparison and your model fit for your data. We will see you soon.